Very good morning. In this video, we will see about optimization technique for training efficient deep models in the course IT22043 Deep Learning and its Application. The main objective of this session is to understand about the nuances of modern practical deep networks. At the end of the course, you can able to interpret the main fundamentals that drive deep learning. These are the books we follow in this video. This is the course syllabus for Unit 2. So, what is optimization? Optimization plays a very crucial role in training deep learning models. It involves adjusting the model parameters to minimize a loss function which quantifies the difference between the predicted and the actual output. So at its core, optimization in deep learning is about solving this equation theta is equal to or minimum of lambda of theta. So here theta represents the model parameters and L of theta is the loss function. Either it can be a mean squared error or cross entropy loss. The goal is to find theta, that is the optimal set of parameters that minimize the loss. One of the most important optimization is the gradient descent. So this we have already seen in the previous videos. So gradient descent is an iterative optimization algorithm used to minimize the loss function by updating the model parameters in the direction of the steepest descent. Since deep learning models have millions of parameters, we use gradient-based methods to find optimal parameters efficiently. So gradient descent updates parameters iteratively using the rule theta t plus 1 is equal to theta t minus eta delta of L of theta t. So here eta controls the step size, which is the learning rate, and delta L of theta t is the gradient of the loss with respect to parameters. The update is repeated until the loss converges to a minimum. There are different approaches are available for finding out the gradient descent. Some of them are batch gradient descent, which will be used and computes gradient using the entire data set. Stochastic gradient descent uses one data point per update. Mini batch gradient descent uses a small batch of data, balancing stability and speed. Other advanced optimization techniques are momentum. Momentum helps escape local minima and speeds up convergence by incorporating past gradients. V of t is equal to beta V of t minus 1 plus 1 minus beta delta L of theta t. Theta t plus 1 is equal to theta t minus eta Vt. So where Vt accumulates past gradient smoothing updates. And the next advanced optimization technique is the adaptive methods. There are different adaptive methods are available. First one is the AdaGrad, which adjusts the learning rate for each parameter individually. Another one is RMS proportionate. So it normalizes updates using an exponentially decaying average of squared gradients. And the most important and popular optimization technique is the ADAM, that is adaptive moment estimation. It combines momentum and RMS proportionate for better convergence. Here it uses the following update rule. MT is equal to beta 1 MT minus 1 plus 1 minus beta 1 delta L of theta t. So Vt is equal to beta 2 Vt minus 1 plus 1 minus beta 2 delta L of theta t whole square. Theta t plus 1 is equal to theta t minus eta mt divided by square root of Vt plus epsilon. So even though optimization are very important, there are many challenges while implementing them. First one is vanishing or exploding gradients. Using proper weight initialization and activation function helps. Next one is local minima and saddle points. Optimization method like Adam help escape from local minima and saddle points. Overfitting. So regularization prevents memorization. Choosing the right learning rate. So learning rate schedule can help. That is step decay, cosine as annealing techniques. So these are the common practices we will follow for using the optimization technique. Use batch normalization to stabilize training. Gradient clipping prevents large updates in deep networks. Employ learning rate annealing to refine optimization, and experiment with ADAM or RMS prop for adaptive learning rates. Thank you.